We are kind of speeding toward the finish line here. Really, here's a little secret that I have. This section is really kind of the last one that I feel like I have to cover in this class, okay? Everything that we've been doing, like with vectors and the first couple of sections in chapter 12 have been building to this point, really, okay? To talk about velocity and acceleration, that's not the only application of the vector stuff, but really a lot of the physical world is described in terms of these two physical measurements, yeah? And so a lot of what we've been doing comes to fruition in this section. Now, I mentioned before that we will also be interested in things like curvature and trying to measure just how curvy a curve is, yes? And then sometimes we have a sense of, when you're driving your car around, and the road goes like this, you're like, oh, that's pretty gentle. But then if suddenly it goes like this, whoop, you're like, oh man, that was a pretty curvy point. And then whoop, like that. Okay, so like this point right here and this point right here, you would expect a high amount of curvature, yes? Whereas here, or even here, I mean, you're pushing the pedal to the metal, correct? You're not really concerned about necessarily slowing down. So curvature is something that we will use to make rigorous what we're talking about when we say things like, wow, that was a really sharp turn right there, yeah? We'll have the tools to do that. It'll be sort of an interesting wrap up to a lot of the things we've been discussing. But this right here is kind of the culmination of things we've been talking about. All right, so let's talk about velocity and acceleration, okay? So T, we often think of, and by the way, I mean, just so that you're aware, although a lot of our conversations here are going to be in the realm of two-dimensional space, all of this can be extended to three-dimensional space. Sometimes it's just easier to start the discussion there, okay? So the vector valued function, R of t equal to, right, x of t, y of t, sometimes we write it this way, x of t, y of t. I know that like last time I was using f, g, and h, but let's just stop horsing around, right? Let's say x is a function of t, so let's just call it x of t, yeah? And y of t. And again, we could also have a third component function, namely z, that depends on time, okay? T can represent time, and this vector valued function can represent position on a space curve determined by this thing, yes? Okay, so R of t, the vector head, that can be our position at time t on the space curve determined by this vector valued function, okay? And therefore, we kind of move along this space curve as time goes on. And we can talk about things like, okay, how am I tending to move at time t, okay? And that's given by the derivative vector we talked about last time. In essence, that is a velocity vector. It tells us how we are moving at time t. What's the direction? What's the magnitude with which I'm actually moving at time t on that space curve? Acceleration, the way I like to think about it, and of course some physicist is going to think I'm sort of a dunce for thinking this way, and that's fine. But acceleration to me is more predictive. This is how is my future movement going to be affected? Does that make sense? Acceleration is talking more about future movement. Acceleration is saying, I'm going to pull you in this direction, and you're going to see how that's going to change your direction over time. Yeah? I mean, after all, if I toss a ball into the air, that thing immediately starts getting impacted by gravity, right? And it's essentially the acceleration due to gravity that's changing that thing. And the entire direction of that ball, in terms of like future direction, is being affected by that acceleration due to gravity, yeah? So velocity is more like a present tense, like this is what's happening right now. Acceleration is more like predictive. It's like what's going to happen in the near future. Does that make sense? I like to think about things that way. It's helpful for me, hopefully for you as well. All right, any questions on that? So velocity, I think of that as the present, okay? Present movement, okay? Acceleration, that's like future movement. How is future movement being impacted? And I would say position, which comes before velocity, position, which is basically r of t itself. I would say that that's just talking about where am I, right? Where am I? And then we want to start talking about what sort of movement is going on right now. That's velocity. And then future movement is dictated by acceleration. Okay? That's kind of a helpful way to think things through, I think. Okay? So if x and y are twice differentiable functions of t, and r is a vector valued function, okay, then the velocity vector, acceleration vector, and the speed at time t are given by these things. So velocity is just the derivative of the position vector, okay, the original vector valued function, which I like to think of as position. Where are you on the space curve is essentially the question being asked here, okay? Velocity is describing how we are moving, right? That's the derivative, and we even use like v of t to notate that. And of course, you know that to get that, you take the derivative of each one of the components. And by the way, I mean, I just want to make sure you guys are on the same page here. You understand that there could be a third component here, yes? We could be in space, and we really are in space anyways, right? Even if it's only a two-dimensional thing, okay? Acceleration is more predictive in terms of how it works, right? So that's the second derivative there, okay? Speed, that is the magnitude of the velocity vector, right? So remember, the velocity vector has both direction and magnitude, right? The whole despicable me thing, right? Direction and magnitude. And speed is that magnitude, okay? For r of t that includes a k component, just add a third term accordingly. No problem, okay? That makes sense. We're going to see some sort of practical outworkings of this by looking at a couple of examples. But hopefully this kind of makes sense to y'all, right? Hopefully. I hope. All right. All right. Going back here. Position vector in an object moving in a plane is given by this equation. R of t is t cubed, I plus t squared j for t bigger than or equal to 0. Find its velocity, speed, and acceleration when t is equal to 1, and sketch a graph. Okay, well, that's interesting. What I want to do is actually go and look at this in GeoGebra, okay? I mean, we could sort of roughly think about how this thing might look, but it's good for us to go over there and to plot various things that will give us insight into what's happening, okay? So let's do that. So r of t is t cubed, comma, t squared as a vector valued function. We want to find the velocity, speed, and acceleration when t equals to 1. And actually, we're going to look at it for general t, just to really wrap our minds around what's happening here. Okay, so let's go in here. Here we are. So what was it? Remember, when we go into GeoGebra, you know, if you want to name something, you can name it. I'm going to put R here just because it's, you know, that's the letter that we typically use for this. Okay, curve. Okay, in this case, I want a couple of expressions. This one right here. Okay, so the first expression, let's see, what was it, t cubed? Okay, second expression, t squared. What's the parameter variable? T. We want a t bigger than or equal to 0. So I don't know, let's go like from 0 to, you know, something that's clearly going to be off the screen, like 10 or something like that, okay? Okay. There it is. There is this thing. So I could actually zoom out if I wanted to and get a better perspective on things, but there's the graph of that curve. There's the graph of that curve right there. Okay. So first of all, of course, x is t cubed, y is t squared. So of course, if x is t cubed and y is t squared, then of course r prime of t is what? I'm not trying to insult your intelligence, but it's going to be 3t squared, comma, t, or sorry, 2t. 2t. There you go. Okay. So, first of all, I think I want to actually create sort of a position vector for this thing, and you know, something that will kind of move us along on this thing. So, so I want to say vector, and I want to do a point like this. I think I'm going to go R of S, and I'm going to pray that this thing actually makes a slider, and it did. Woohoo! Yeah. Okay. Sometimes if you put like a little slider in there, it will automatically do that. It's not a good idea to use the same variable that you use to sketch the curve. This is a parameter that's going to move us along that curve. Okay. And here I want to go. So you see that vector? See that? See that thing kind of moving along there? First of all, I don't want the left-hand end of this thing to be 5. I want it to be, what was it, 0? And I don't care. We could go up to 5, but we're not going to really see beyond that anyways. But why not? Let's go up to 10. Okay. And of course, I can play this thing. And by the way, you can speed things up if you want, right? I don't know. It's probably not necessarily. I could go to 1. You can even have this thing like by default, it's just going to oscillate back and forth like this. I like it to kind of go and then start over, like continue to start over as we do this. I'm just trying to show you how this thing works in some sense. Here, if I pause this and I go in here and I go to settings, I think that I can go to the slider settings right here. And I could tell it right here, it says oscillating, where it kind of goes back and forth through the parameter. How would I change that? Which one do you think I want? Oscillating, always increasing, always decreasing, increasing only once. Increasing only once means it will only go through one time. Well, I like to just do increasing, okay? Like that. And then you can play this thing, and I'll speed it up a little bit so it goes through, you know, rather quickly, but here it goes. You see that thing like that? Okay, so there's the terminal ends of this thing. By the way, you know, maybe I don't care so much about this thing going to 10 for crying out loud. Let's just go to 5, okay? Like I said a couple of minutes ago. So you just see it going like that. There's the sort of position vector, right? Okay. Now, what I also want is I want the derivative of this thing. Make sense? Yeah? And I think I'm going to try to actually name it. Maybe I can, man, it looks like it already knows what that means, right? Do you see R prime? It kind of has that right there. Let me see if I go R prime of T. Huh. No, that's a little bit surprising to me. I'm just going to use a different letter. Okay, like W equals curve, and I'm just going to type this thing in manually. Okay. So what's the first expression I should put in here? Yeah, 3t squared. Okay. Second thing should be 2t. The variable is t. The start value is 0. The end value is 10. Okay. And that curve just got sketched. I don't care about seeing that curve. What I really want is I want a vector that has values equal to that for various values of s. Does that make sense? Yeah? Okay. So what I'm going to do here is I'm going to go vector. Okay, now I want a start point and an end point. You understand? I want this thing to actually go from the end of that vector and show like the tangent vector at this point. Yes? So it's going to be a vector that starts at R of S, okay, and ends at R of S plus W of S. Okay? Okay, now hopefully you can kind of see that. Boy, I don't know, maybe you can. You see there's like two vectors there. One of them's the position vector, one of them's tangent vector. Maybe if I get rid of the position vector. See that tangent vector kind of shooting along there? There's the tangent vector and it kind of goes up like that, yeah? If I could, I could actually change the color of this, I think. Settings, I go to color. I don't know, maybe I'll make a red. Maybe I'll make it red so it really stands out, okay? See, so there's that tangent vector kind of going along there. Do you see that? Okay, there's that tangent vector going along over time. And I'll put the position vector back in here. I'll color that one blue. I don't know, I'm just really messing around here right now. Here's blue, okay? So now I have my position vector and my tangent vector going on there. You see that? Yeah? Okay, lastly, I want acceleration, okay? So acceleration is going to be the second derivative of this thing, okay? Let me go up here. Okay, this was the original guy. So like R of t was equal to t cubed, t squared, okay? And then R prime of t is equal to 3t squared 2t. That's velocity. Acceleration, well, what's that going to be? Yeah, 6t2. That's simple. Okay? 6t and 2. So I go down here. I'm going to make another one. Why not? Okay? Man, I don't know. I'm kind of running out of letters here. I'll let it kind of determine things for me. So I'll go curve. Okay, expression. I'm going to go 6t for the first expression, 2 for the second, t, 0, 10. Okay. So there is the acceleration thing. I don't want to draw this as a curve, but what I really want is a vector that's going to represent acceleration. So I go vector, start point. Okay, where do I want this thing to start? I want to draw this thing from the point on the space curve, yes? So I want the vector to start at R of S, okay? And then I want it to go to R of S plus this guy right here. I guess it's A of S, right? Oh, cool. They used A, which is like, oh, amazing. That's, oh man, look at this. This is V, yeah? Velocity. I didn't even plan that. You know what I'm saying? And this is A for what? Acceleration. That's cool. Hey, what do you know, right? Okay, so A of S, like this, okay? Let's watch what happens with that. Can we even see it? Yeah. Okay, so that's the black thing right there. But let's you know, let's color that thing green or something like that. Lime green. Okay, lime green. Okay, and we'll kind of erase this stuff. We'll move this over so we can get a good view of what's happening here. Why does this thing make sense? See, do you see the green arrow? What's it basically doing? The green arrow is supposed to be kind of predicting future behavior. Do you see that that red arrow is kind of slowly turning like that? Yeah? So it makes sense that the green arrow is inside of that. It's kind of yanking it in that direction just slightly. Does that make sense? And also, what do you notice about the red arrow as time goes on? Is it getting longer or staying the same length? It's getting longer, and that makes sense because the green arrow is actually pulling in the same general direction as the red arrow. Make sense? Yeah? So the green arrow is kind of pulling inside, which causes the red arrow to, kind of move in that general direction. And it's getting longer because the green arrow is pulling in that same general direction. Yes? So you can kind of see that the green arrow is kind of saying, this is what's about to happen. The green arrow is saying, we're going to be going faster, and it's going to be curving us in that direction. Yeah? So you see velocity with the red arrow, and you see acceleration with the green arrow. Does that make sense, hopefully? So you can kind of look at that. It's pretty cool, right? See it? The green arrow like that, right? Okay, so hopefully that's instructive. Okay, here we are in three-dimensional space again. Cool. I think that's pretty cool. I don't know. I could stare at that all day, but that wouldn't be very productive. Okay. Any questions on that? Questions? All right. So GeoGebra can really help us visualize some of this stuff. I think that's pretty helpful. Okay. So find its velocity, speed, and acceleration when t equals 1. Look, seriously, that's going to be very easy. Okay. So let's just quickly do that. We just looked at this thing graphically for all values of t, but you know, r prime of t is equal to 3t squared, 2t. Okay. So so what is, okay, the length of r prime of t, which by the way is the speed at any time t, is given by, okay, hang on a second. It's given by the square root of the square of the first thing plus the square of the second thing, yes? So this is going to be 9t to the fourth plus what? 9t to the fourth plus 4t squared. Yeah, you just square both of those things. Okay. So the speed, so let me just to notate this, I'll say this is like s of t for the speed at time t. And we were asked for the speed at time equal to 1, which is going to be the square root of 13, whatever your speed units happen to be. Okay, what is the velocity? Okay, so here's v at time t. Okay, so the velocity at time 1, of course, is just going to be 3, 2 as a vector. Okay. And what about the acceleration when t equals to 1? Well, that's easy. I just need to take the second derivative. We call that a of t. Okay, the second derivative is 6t, 2. So the acceleration at time 1 is just going to be 6, 2. Okay? That's it. That's very quick. And we already looked at this thing graphically, and it made sense to us seeing the acceleration, velocity, and position vectors interacting with each other. Yes? I think that's kind of a neat thing to look at. Any questions on this? Questions? Any questions? Well, moving on. Describe the motion of an object moving according to this position function. Okay, r of t equal to 3 sine t, 3 cos t. So I'm going to write this down, and we'll go over there and mess with this for a minute. Okay, so this is 3 sine t, comma, negative 3 cosine of t. Okay, so let's take a look at this. Go over here and we'll take a little gander at what's happening here. Okay. So let me kind of turn off some of these things. In fact, you know what? I'm going to go ahead and just open up a new one of these. So again, this is Geogebra 3D. Okay, here we go. So 3 sine t, negative 3 cos t. Now, let me just ask you, what is this curve going to look like? Again, we're doing things in 2-dimensional space right now, but it's living in 3-dimensional space. What is this going to look like as a space curve? What's it going to look like? It's going to be a circle of radius what? 3. I know that x and y have been flipped around, but it really doesn't end up mattering in the end. That's just going to determine sort of orientation around the curve as we move. But in the end, it's still going to be a circle of radius 3. Okay. So I'm going to let GeoGebra work its magic, but this is 3 sine. Usually it likes it when I put a space in here. 3 sine of t. Okay. Negative 3 cosine of t, parameter t, 0. Let's go 2 pi, right? That you know that you don't need to go any further than 2 pi. And there it is. Okay, so there is the space curve determined by that, yeah? Not surprising. Just so we can sort of keep track of the point moving as t increases, what I do is I go vector, and now we're just going to do a point. It's going to be a of s, where s is kind of a parameter. I pray that they give me a slider. They do. So this goes from 0 to 2 pi. Okay. And now I want to change this thing so it's always in the increasing direction. Okay. Becoming sort of expert at this. I'm going to leave that thing colored black. We'll watch this thing move over time. Okay. So look, there's this is like the typical orientation we would see. This thing is going around in the counterclockwise direction. Okay. Although I think our starting point might be a little bit different than usual. Let's see. Oh man, what's going on? Pause this thing. If I go back to 0, the thing starts pointing down, but then goes in this counterclockwise direction. If I plug 0 into this thing, sine of 0 is 0, correct? Cosine of 0 is 1, so our y coordinate's -3. So it makes sense we start there. Okay. If we go, there's our position function. Let's do the derivative. Okay, and let's kind of do it on the fly. What is the derivative of this thing? So r prime of t is what? 3 cosine of t, 3 sine of t. Excellent. Okay, so let's sort that out. We're gonna go curve. Okay, we need a 2 expression thing. It's gonna be 3 cosine of t. Oops. Okay, 3 sine of t. Okay, parameter variable t. Start value 0, end value 2 pi. Excellent. We don't need to necessarily graph this. We just have this because we want to make a vector. A vector, and I want this thing to start on the position. At the position, right? At the end of the position vector, yes? I want it to kind of start from there so I can keep track of what's happening. Okay, so my start point is going to be, oh man, what did they call this thing? What's the start point? LOA. Okay, so my start, oh, are you serious? They're gonna make me start over now. Good grief. Okay, vector, start point A of S, end point A of S plus, I need B of S, right? So this thing right here, okay, B of S. Okay. There it is. See that? That's cool. There's the velocity vector at each point. Let's color that a different color. I don't know, red. Okay. Color red. That's great. I think that's red. Okay. All right, so we have that. Now let's talk about acceleration. Okay, so of course our double prime of t is equal to, this is, okay, becoming easy now, -3 sine t, comma what? -3 sine t, 3 cosine of t. Now, let me just ask you a question. Doesn't that look pretty similar to the first guy? Doesn't that look pretty similar? What's the relationship between the second derivative and the original? They're negated. So it's negative, the position function. But doesn't that make sense? Think about it. I mean, what would you predict about the acceleration? Look at how we're moving. This thing looks like there's something kind of yanking it to determine its future direction. Like this thing is curving like this. Why would that be happening? Well, something's yanking it in that direction. If we were in a car, it would be our steering wheel. Do you know what I'm saying? That would kind of be the force that was causing that to happen. Okay. So you suspect, and this is going to get sort of awkward. Let me. Oh man. So yeah. So how do I want to do this? I'm going to go. I'm going to go like this. Vector what? What would be the start point? Well, it would be A of S, comma A of S plus. Well, what do I want to do? A of S. Okay, where do I want to end this thing? That's it. A of S minus, hang on a second. I want to do the negative of this vector, right? But I want it to start from the other thing. 0. Oh yeah, so it would just be 0. Okay. A of s minus A of s, which just happens to be 0. Yeah. And that's going to give 0. Illegal argument. Oh, I see. 0, 0, 0. Okay. Now I think it's going to work. It's going to go backwards. I am going to get rid of, well, yeah, actually, I'm going to get rid of the position vector, okay? Because the position is already made clear by the actual tangent vector, correct? So let me kind of change the color of this just so you realize this is acceleration. Okay, so maybe we'll turn this guy green or something. Yeah. Cool. So there is our acceleration vector. Doesn't it make sense that we're being accelerated like toward the middle of the circle? Yes, that's what's kind of keeping us on the edge of this circle. And notice, are we ever going faster? No, we're not ever going faster, right? That is because the acceleration vector is basically constant here. Does that make sense? If the acceleration vector actually was getting longer at certain points, you would see the velocity vector start to creep up. If that makes sense. Yeah, that's interesting. I don't like the fact that there's a label on this. You can always get rid of that by going like this. Okay, and there we have our acceleration and our velocity vector at the same place. Look, I'm sorry, I'm obsessed. I don't like that color. I want to be able to see it better. Let's do, what's that? Right here? That's what that is? That's going to look worse. Forget that. Okay. Boy, I don't know. Oh, that looks a little bit better, I guess. Yeah, we can definitely see that stand out. Okay. Cool. All right. I think this is kind of cool to kind of think about these sorts of things. Okay. I think right in this particular context, I think this is where vector stuff really starts to make sense. Yeah. And this is where velocity and acceleration and things really start to come together in our minds. Okay. So this is good. Good for us to think through. No question. All right. All right. We're done with that. Well, I'm actually, believe it or not, I'm actually kind of done. Okay. We'll talk about projectile motion tomorrow and actually solving the equation for projectile motion tomorrow. Yeah. And then we'll be done with section 3. I'm done. Can we just play dodgeball and all projectile motion?